Hi. Wait, where did my big old thing? Is it possible? Yeah, yeah. So, for example, like this is what I'm saying. Like this thing, this proof needed n to be an integer. Oh my. Thank you so much. Um Nonetheless, this thing is true. It's still true that ddx of x to the n is equal to n times x to the n minus 1 is true for all r, or sorry, for all n in the real, for all n real. Yeah, this proof is not true. It doesn't work when n is any is a non-integer. Yeah. Nonetheless, it's still true that the fact is true for no matter what value of n you pick. So like x to the pi has a derivative which is pi times x to the pi minus 1 power. Hi. Hello there. Hi. You got a math question? People out there, if you have a math question, please feel free to ask. It doesn't have to be some highfalutin question. It doesn't have to be like super hard or anything like that, or anything like that. Even if it's very simple, I want to help you. And you know why? Because I love you. That's why. Hummers, what should I do? Thank you all for hanging out and asking such cool questions. Callum, I researched something called hyperbolic geometry. Hyperbolic geometry, like you probably at some point in your life have learned geometry. Geometry can mean many things, though, the deeper you go in mathematics. And one of the types of geometry that is very interesting to mathematicians is something called hyperbolic geometry. It's hard to describe the reasons why right now, but that's what I studied, is hyperbolic geometry. I love philosophy. Please do. This music is loud. This is one of my favorite bands, Unwound, but this music is a little too intense, huh? Spotify. You think circles exist in the real world, or are they purely a mathematical abstraction? I do think they are a mathematical abstraction. But it seems like what you're asking then about are like what things are real and what things aren't. I kind of tend to think that mathematical ideas like numbers, circles, equilateral triangles, I tend to think that those things exist. I can't point to where they exist, but I think that patterns of thought are real things, like things that we think are real things. So even if something is quote unquote purely conceptual or whatever, I'm not sure that that really has an enormous bearing on whether we should consider that thing to be real or not, right? Like the word real there is what's, I think, I'm doing a lot of work. It's of a different character, certainly, than like chairs and tables and all of that. But you know what? You know what? Even when it comes to stuff like chairs and tables, like what is a chair? Can you tell me what a chair is? Like ultimate, so like if you point to a chair, what are you pointing at? Because, ultimately what a chair is a collection of subatomic particles arranged in a particular way, which for some reason we've deemed, we've put into a category chair. Do you see what I mean? So, are chairs real? Or are they purely an abstraction? I kind of think chairs are real. I want to accept chairs into my what they call ontology. But I also have to admit that the scientific view of the world that we've been given, particularly in the 20th century, is a bit undermining of all of this, right? Just a bit. So there was a famous American philosopher named Wilfrid Sellars, Sellarsa at the end, and he talked about the what did he call it? He talked about the manifest image of the world and the scientific image of the world. And like, how do we reconcile these things? I think that's a super interesting question. I'm kind of going in a different direction, aren't I? I'm sort of moving away from the math thing. But I find that question super interesting, right? Because I feel like there's something, even just in the usual objects, that I feel like our intuitions would suggest are totally real, like glasses on, like my cup on the table. Like, this is real. This is a real thing, right? But then you learn about the scientific image of the world. You learn about things like, at least maybe you don't learn in any depth, but you know that, the models that we have for our world suggest that everything is, a conglomeration of particles, and these particles are like vibrations in certain quantum fields and all of that kind of stuff. And it sort of presents a different view on the world than maybe you've been accustomed to. And when you have that shift in view, I think there is going along with that a shift or a possible change in how you might respond to a question like, is such and so thing real? I don't know. I think that at a point that the mathematics are able to dictate the physics of our world, like Newton's equations of motions, this validates mathematics just as real as what surrounds us. So then we get into questions of accuracy, right? Because you should know, Callum, and I'm sure you'll learn this if you don't know it already, that in fact, Newton's equations are undermined by Einstein, right? Like Einstein came along, for example, if you're looking at like Newton's gravity, theory of gravity. Well, it's not right, but it's pretty dang close, right? And it's good enough for good enough for in using an almost in a tremendously wide and diverse array of applications and situations and such. But it's just not right. It's not the right model of gravity. We know that now. And so we have a better one, which is Einstein's general relativity. And so Newton, in that way, his discovery, though tremendous, has been, somewhat supplanted. Not, but we still learn that stuff for a good reason. You can probably think of why. But there, like, is it really the math that's happening there, or is it just like sort of what Exavention's saying is like a language and that we use to model? That, in other words, is the math just sort of a reflection of the physics? Mathematics is just a convenient language in which we model the behavior of nature and physics. There could be a better language, we just haven't found one yet. If you talk to, or if you read about, like, Buddhist philosophy, right? Then they'll say things about the limitations of language, period, of any language. I agree with you in a sense, Exavention, but if you think about the reliability and consistency in all forms of mathematics, a human couldn't realistically fabricate these numbers that mean nothing. Oh, there's so much to say. I guess it falls into the arena of whether mathematics is our language or the language. How to deal with the idea that space-time has a minimum length at the same time as taking the limit of the number of sides of a shape to infinity. I mean, there are definitely people out there that think that, I mean, I've not read this book, but there's a dude. What is that dude's name? Is the dude's name Tegmark? Or am I mixing him up with somebody else? There's somebody that believes that the fabric of reality is math. Like, there's no layer of, like, modeling. It is math. And I haven't quite investigated the arguments in favor of his thesis, but the idea is at least out there that there are some very hard-nosed mathematical realists out there. Oh, really? There are failures? Okay, maybe I didn't realize that. There are, oh, sure. Okay, fair enough. Fair enough. Yeah, our mathematical universe, right? That's okay. I don't mind at all. Random question. What's my favorite axiomatic set theory? I only know of the one, if I'm going to be honest. So I'm going with that one. Do they call it ZFC? Is that what it's called? Sorry, I'm eating walnuts here. I can sort of understand why people go into the mindset of the earth is flat and we're all in a simulation controlled by gods. because everyone gets to a point where they just don't know and wants to be comfortable in their thoughts. I agree. Yeah, I agree with that. I'm not sure what's uncomfortable about the Earth being round, though. That one strikes me as odd. But certainly, when it comes to question of like religious questions, or questions that seem unanswerable, like what's the point of it all, that sort of thing. I can understand that one can improve the quality of their life by relying on some preformed answers there. So I understand the impulse there for sure. I, for some reason, am very resistant to that kind of stuff, but I don't know. That's only me. Hello, ladies and gerbils. If anybody out there has a math question or any other question or any comment you want to make, please ask here. Yeah. Can I explain what useful operations differential topology provides to the applied differential geometer? Well, I mean, it's kind of like differential topologies. I mean, the way I view it is that differential topology, although it does sort of go off and do its own sorts of things, like Morse theory and stuff like that, I kind of view differential topology, at least the basics of it, as being like a prereq for differential geometry, right? Like you need to know what the tangent bundle is, a cotangent bundle, all that stuff, right? Like that strikes me as being a more topological, those being topological concepts. And then, of course, you decorate that topology with geometry, with like the metric and stuff like that. But differential topology, it does have its like own results, like Morse theory, like I said, and things like that, which are really cool. I don't, and I mean, there's some very useful sorts of intersections, right? Like certain topological invariants showing up as nice little geometric gadgets. This gets a little bit technical, but there are like things like yeah, the definition of manifold is topological, but does it provide, quote, this one neat trick that makes certain kinds of geometric analysis easier? I don't want to say no. Rather, I want to say uh, I don't know. Well, so I mean, like, like there's things like characteristic classes, which are certain cohomology classes, which arise in a topological context, but can be used um, in a very geometric way. Uh, there's things like, well, maybe that's a good example. I don't know. I know you've obviously studied mathematics, but could you show me a hard calculus problem that you could expect on a mechanical engineering degree if you know what it could entail? Um, mechanical engineering. I'm just thinking. I'm thinking is what I'm doing. So like there's interesting derivations that you can do in there's interesting derivations for like stuff like free fall. Like free fall is really easy when thinking about the free fall of objects, say. But things get more complicated when you toss in certain assumptions, or that is to say, you maybe remove certain assumptions that you might make to make the answer really trivial. What am I talking about? I mean, like if you have free fall, but with air resistance or something like that. This is a very commonly cited problem in differential equations. Now, differential equations, I think, should be pretty naturally viewed as like a extension of calculus. But the idea is that let's see if I can conjure this model here. Like if you've got an object of mass m and it's falling, then sometimes what people will do, especially like in a first physics class, yeah, this isn't really mechanical engineering, right? Mechanical engineering, okay, this is my understanding, is that in a day-to-day, the day-to-day workflow of a mechanical engineer, particularly one concerned with design, is that they put stuff in a CAD machine, or a CAD program rather, which is like a design program for building structures and stuff. And then, as Exavention mentions, you get your computer to perform what's called a finite element analysis of that thing. It's not really so. I like what's going on under the hood there is a whole lot of linear algebra. Basically, you make continuous phenomena, or things that we could in principle model continuously. Things like forces acting in with varying, let's say, intensity across a particular beam in a bridge or something like that. You subject that to like an earthquake or a simulated earthquake or like a simulated windstorm or something like that, and you see whether it will collapse and kill everybody on the bridge or not, right? And the way that you simulate that kind of stuff is you approximate your continuous object, your beam or whatever, using finite element analysis. What it does is it transforms the beam into like a graph with a bunch of nodes and edges. And there are rules, like basic computational rules for how things propagate through time in this kind of setting of a grid. How, for example, how heat might be distributed or something like that. There are ways of taking continuous problems and making them finite. Yeah, of course. So you can link. Sorry, I realize I read things and then just respond to them, but I should just I need to point out the things that I'm reading, or else it's confusing. Yeah, so finite element analysis, but that's really, I think, much more falls under the category. Maybe I'm wrong. I feel like that falls under more of the category of linear algebra, which is a subject as a mechanical engineer you'll certainly be learning about. Yeah, that's not a good example. Hello there, friends. If anybody's got a question about math, be it hard, be it easy, why not ask in chat? We've got a good group of people here that are more than capable of helping, I think, particularly with simple questions. Harder questions, no guarantees. Do I think P equals MP? I'm going with what it seems to me is the consensus opinion of the computer science community, which is that P is not MP, although they can't prove it. So I'm going with that. I'm not enough of a ballsy contrarian to go against that. You know, I knew a guy, I don't know if this is relevant, but I knew a guy who would attend our topology seminar. And this was before Perelman. So before 2003 or so, when Perelman came out with his revolutionary proof of the geometrization conjecture, and hence proving the Poincare conjecture, who believed the Poincare conjecture was false. And he believed that there was an exotic three sphere that, was homotopy equivalent to this sphere, but not homeomorphic or whatever. At the moment, I am just worried about it. Total contrarian, because at the time, everybody believed that the Poincare conjecture was true, and everybody except this one guy that I knew. He was a pretty senior mathematician. A topologist. He was like a student of Moore's at UT Austin, and he lived in around Berkeley, and he would come to the topology seminar. But he was very fond of saying that he didn't believe in the Poincare conjecture. He turned out to be wrong. At the moment, I'm just worried about the curriculum stuff. Everywhere I read about people who have studied it, and they say it's very hard. But I have nobody to ask specifically about what sorts of things I can expect, really. But I am glad I found you guys here. I'm here to help, absolutely. And I bet many other people in this chat are very keen on talking about this stuff. So, yeah, anytime. Very few math guys get formal theoretical computation training. True. That said, it is a pure math field. It is usually just studied by computer science guys. True. There are significant dissenters like Knuth. Oh man, it's hard to go against Knuth. But you have to wonder about the calculus of these things for a guy like Knuth. Say he's wrong, and it's proven that P is equal to MP. Or sorry, P is not MP. And it's kind of like, okay, but he's Donald Knuth. And maybe it's a little bit of a chink in his armor or whatever, but if he's right. I don't know. That seems like a very big deal if he's right. He gets a lot of credit there, right? For something. I don't know what it is. Like there might be in other words, I'm saying there might be an incentive for a guy like Knuth to take the contrarian position. Because it's kind of fun, and maybe it just increase the legend of his stature. I somewhat doubt he thinks about it that way. He's not really that kind of person. Okay, I don't really know. I really just made that up. I only know the guy from because he wrote Tech, right? The typesetting system. I know he's an incredibly great computer science dude. Hey, if anybody's got a question about math, be it hard or easy or whatever, ask in the channel. And thank you to everybody who is hanging out. We've been talking about lots of different kinds of stuff. It's been fun. I'll probably be here for the next hour and a half or so. Oh, and the Twitch bio. Sure. Oh, but see, the problem is, I think that Discord links invites, they expire. Do they not? Maybe I should be like pushing this link, not the Discord link, but the link to this chat around, you know? Anyway, if you want to join a Discord. Oh, and earlier today we had a very, for the first time actually, we had a good chat, Callum and I, over voice, and I think that was productive. Yeah. Really, what I should be doing is spreading around this Twitch channel URL. Like, I probably need to be hitting up subreddits and things like that. Somebody, I think Free Apple Pies, was kind enough to drop the link to this stream in one of the subreddits. I can't remember which. I think it was Learn Math. But there are other ones that are geared toward somebody said that mentioned the cheat at math homework or something like that subreddit. So maybe it would be beneficial to have something posted there. Wow, Wolfram's a crackpot? Like, I know that that big thick book that he came out with about cellular automata was sort of panned by the community at large. I kind of liked it. I liked flipping through it. I mean, I was able to get it for like $5 at a used bookstore because they had so many copies. A lot of people, I think, I don't know how much the book cost when it came out, but it is enormous. It is like the biggest book that I have on my bookshelf. But and it was kind of panned, and I think it was because like a lot of the stuff that Wolfram, like, it was kind of overhyped by Wolfram, like this is the secret to everything, sort of thing. And it wasn't all that, according to the reviews and the criticism that I was hearing. It wasn't all that original or anything like that. It was, most of this stuff had been known, but I thought it was pretty. I didn't know about a lot of this stuff. I thought it was pretty interesting. I don't know that it's the magic bullet that solves all the problems of physics and things like that, but I thought it was cool. Wolfram is an accomplished particle physicist, but he's been out of the field since his mid-20s. He knows what he's talking about, but I think he just spitballing non-rigorous ideas for attention. I heard he had a proposal for like a theory for everything or something like that involved like graphs or hypergraphs or something. And I think in looking at it, what my impression was, and this is take it with a grain of salt, but just to talk about it, my impression was that it was very like an abstract framework for maybe talking about physics, which might be useful, but it's unclear whether or not that will actually lead to new insights or whatever. I'm not sure. I'm not. I feel uncomfortable even talking about it because I don't want to. I don't want to say the wrong thing, but that was just the feeling, the sort of vague feeling I got when I looked at the complicated graphs and set of graphs that he had. And Mathematica is a pretty good piece of software, even though it's expensive. Hey, if anybody's got any questions about anything, just drop them in chat. And while I'm waiting, I think I'm going to play, or I think finish a run that I started yesterday of Slay the Spire. Let me do some editing of my stream info. I've been experimenting with trying to sit in different categories on Twitch. Yeah, the reviews I've seen indicate it's not useful, but maybe he just isn't finished yet. I don't know. Andril from Narsil is right that he's not really doing physics, but I wouldn't call him a crackpot. Using Leibniz notation in differential calc, we develop lots of shortcuts where it feels like we use dy dx as a fraction. Am I right to be concerned about developing bad habits? I kind of think it's okay. But then when you actually get to learning differential forms, you're going to be okay. You're going to be fine. Yeah. Yeah, like the chain rule. That sort of thing. Hi, Uncle Bill Druin. Welcome to the stream. If you've got a math question or some such, or just anything you want to talk about, why not do it here? Why not? Yes, that's right. I have to admit, I'm ever so slightly emote illiterate. So, not quite sure what eyes mean in that context. I hope it's a good thing. My excuse is that I'm 42. And this emote stuff, this is some Zoomer stuff, right? This is my excuse, okay? Oh wait, I got this. I got the text thinger. Maybe I should just sort of lower this to make it a little bit more visible. Oh, cool. Okay, I like that very much. Oh, you are the supreme leader of that thing. Okay. Yeah, I put a post in there introducing myself today, um, and sort of my plan or my vision anyway, um, for this stream. My hopes for this stream, I should say. It seems like an interesting community. I'm surprised. Well, surprised, but actually, first of all, I'm surprised that such a conglomeration of streamers like that exists. That was an interesting little discovery. Somebody, um, some I always forget his or her name, John Dre something, came by and mentioned the Discord to me, so I dropped in. Um, but yeah, I was surprised that it exists. Pleasantly surprised, but also I was surprised that there seemed like there were kind of very few math folks in there. It struck me that way anyway, but maybe I'm wrong. A servant leadership role. Okay. So anyway, this is I'm gonna try to finish out this run of Slay the Spire that I started yesterday. For those of you that don't know, yeah, the knowledge foundation, as I understand it, is like a sort of organization of streamers who all of whom are dedicated have dedicated their streams in one form or another to educational purposes. So you have lots of it's not just STEM stuff. You have folks that do like social science and even things like history, even things like very practical things like leather working and that sort of thing. So uh, this stream could be a fit in there, which is why somebody dropped the link into. Oh, fellowship. Foundation implies funding. I don't. Okay, sorry. My bad. Can I show you how to do orthogonal function expansions of a green function for a linear PDE operator? Um, I feel good about the first part of what you said, but like the second part of what you said, um, feels like I'm out of my depth. So I'm gonna pass on that one. Exavention. Yeah, I don't want to say something stupid, or I don't want to mislead you or say something that is confusing or whatever. Oh, by the way, somebody asked how old I was earlier. I'm 42 years old. This that. This that. I can't do. What did I just do? What? I played neutralize and I played a something. I can't remember. Um, for those of you that don't know, Slay the Spire is it's it's a deck building card game. It's a solo game where you're playing against a bunch of fixed opponents, kind of fixed. I mean, the set of opponents is fixed, but there are some that they change from game to game. Sorry, I get distracted easily. My brain gets hijacked easily. So I think this is what I'm gonna do. Hi, Prutz. Good to see you again. We're gonna do this to poison the heck out of this dude. I think we'll do 2 apparitions. I mean, yeah, that's what I have to do. I think that I want to keep after image for last, because then I'll get my orichalcum in. So this thing, if you don't have any block at the end of your turn, then you'll get 6 block. How you doing, Prutz? Oh yeah, boring math professor. I know. I don't know, or I've seen boring math professor. I've not seen Professor Peter before. The token viewer of the 3 founders. I see. But maybe I play blur. Yeah, also I can play these 4. So then it really doesn't make any difference. I'm not sure what I was thinking. There's the catalyst. Kunai. Oh. And yay, he's dead. Dead. Hey, Snecko Skull's good for me. There's a speed potion. Ooh, do I want this one? It feels okay to me. Okay, I'm gonna take it. I don't know what I'm doing. Oh, I can't smith. I can't rest. I guess I'll do this thing. Physics though seems like a cool guy. But I keep saying how I will occasionally visit his stream, and he's up there in front of his blackboard, and I don't have a single clue what he's doing. I don't get it. Boring and Peter are both on the server, and we encourage manual shouts out of them or any other EDU you find. There is significant time lag before a committee rule comes to a consensus on whether a channel should be officially featured or not. I've learned some QM, yeah. Nobody else understood the path integration either. Okay. Oh, I messed that up, but anyway. His particle physics tangents are a little more than I feel like digesting while I'm on Twitch sometimes. I'm not huge on quantum. I don't know. I don't know RuneScape very well. I would imagine that I kind of get the feeling there are sort of in jokes or whatever that I'm not privy to in this game. Just maybe because I don't know the references or whatever, you know. Yeah, Pretz, I don't know if that's just the nature of physics. Sometimes I wonder. Like maybe that's just the way physics class is, you know? And you can't say which steps in particular. You dropped out from college and you never quite got ODEs. Oh, I like ODEs. They're kind of cool. If you got a question about them, ask here. How do you get the idea behind them? Well, so I mean that's a tough question because ODEs span a very large swath of mathematics. And it's hard to so like my feeling when somebody asks a question is what's the idea behind x or y. It's sort of the response that I want to give them is sort of what it all means or something along those lines. uh Maybe that's what you're getting at. I don't know. I know how to solve them, but I don't know why I'm separating variables and things like that. A lot of the stuff that you probably learn in an introductory differential equations class has to do with just being able to solve differential equations. Um, the idea is that you're given a differential equation and you have some that and you can recognize the form of the differential equation and solve it using the appropriate method of solution. I don't know if that helps. But the point, I would say, of differential equations is that it naturally applies ideas from calculus and linear algebra to very physical problems because it's just a fact that a lot of times the physical laws that we have, that humanity has, are given in terms of differential equations. It's kind of natural for that to be the case when you realize that derivatives, what they sort of do are they measure how things change, right? And so it's natural to have laws which say something about the nature of that change. Because after all, our universe is changing everywhere all the time. So differential equations are just a great way of modeling things that change. So you have basic ones like the temperature of a cup of coffee in a room that is of a different temperature, right? There's going to be some loss of heat, for example, you would imagine. And the coffee cup will get colder. And you can ask, well, as a function of time, how does that coffee get colder? And then there's something called Newton's law of cooling, which is a physical law, empirically verified, presumably, which you can use to model that phenomenon. So that's why you're doing it, is to solve those kinds of problems, I would say. And the reason why you do what you do in differential equations class is to be able to, when given a differential equation and other data, solve it. That disturbs me so much. What is it that disturbs you? Is it the fact that everything's changing all the time? You just do things and check the results. Yes. This apparition is pointless. I don't find it circular. I mean, maybe it's circular in the sense that you can refine your model or whatever and make it stronger. But the idea is that you're making progress. You don't need to check your work if you're super confident. Wow. True, I guess. Oh, no, no, no. Do you mean like, how did Newton come up with his law of cooling? That sort of thing? Or do you mean like you don't understand what's behind a particular method of solving a differential equation? Do I want to use this? Like, where does Newton's law of cooling come from? I don't know the precise story, but I would imagine it's very much empirical. Outmath neurologist in a beta plays this game a lot. Wonder if you can outmath his gameplay. I don't know. I find this game very difficult personally. I'm nowhere near an expert in it, but I used to play it a lot maybe a year ago. I kind of dropped it, but I figured it was a nice little diversion for this stream. Olha Trasdevoch said this earlier. I know how to solve them, but I don't know why I'm separating variables and things like that. I mean, that one's hard to. It's like you're doing it because ultimately you're going to be integrating, and that's just what one does. This is not a very satisfying answer. That's one way that one can approach the problem of solving certain differential equations for sure. For sure. So the goal there is purely mathematical, right? To solve it, and there's any number of ways that one could go about that, but you learn about all sorts of different techniques. Yeah. Take it easy, Callum. Good luck with your studying. Get good sleep. It's uneasy that it's not irrefutably proven. Where did the math fit in when you see something? Do you need to separate variables for ODEs? I thought this was only used for PDEs. Well, you certainly can separate variables in some ordinary differential equations, but not all. So they're given names, right? Like there are the separable equations and then other equations. Theorists tend to use Lagrangians to find equations of motion. Yeah, that's something I need to learn at some point in my life. Because we had classes to do things and we were supposed to make models from real life situations. I see. Well, sometimes, sometimes things, sometimes these models come from previously determined laws. So, for example, there is a common problem that I've taught before in a differential equations class, which is, and I talked about it earlier, which is free fall with drag, air resistance. And I'll get to that in a sec, Kappa. But like if you have an object which is falling under gravity, then you can write, and but you also have an opposing drag force. So you got a gravitational force which is pushing the oh wait, you can't see any of this, which is pushing the thing down. One moment. But another force which is a drag force which is going against the direction of motion, like this. Then you can model this situation using like Newton's second law, right? Newton's second law says that the net force is equal to the mass times the acceleration, right? So with these things, you can write down a differential equation for the position, because you know that, for example, right, like acceleration is the second derivative of position with respect to time, right? Oops, I'm doing something wrong. There we go. D squared S dt squared. And as long as you make certain assumptions about these forces, for example, we kind of know what this one is, right? It's just mg, where g is the acceleration due to gravity. So we have mg, and we'll consider that positive. But then we subtract a drag force. And so we make certain assumptions about what that drag force looks like. One assumption that's, I think, pretty common is to assume that the drag force is some quantity which is proportional to the velocity. So you write some proportionality constant times ds dt. And then what you have all of a sudden is a differential equation, right? You have a second order differential equation in position, which you can use if you can solve this, which you can. You learn how to solve it. You figure out what the time trajectory of this, the trajectory as a function of time of this object is. Yeah, sure. No problem. Yeah, it's a what do you call it? It's a homogeneous second order linear differential equation with constant coefficients. That's right. You assume, I think Exavention mentioned this up above. You assume that the solution is of the form e to the RT, and you work it, and what you find is you get this thing called a characteristic polynomial, the roots of which correspond to your solutions. Yeah. Do I use catalyst now or later? Do I use piercing whale now? Yeah, no problem. I think it's a really cool subject, personally. For me, ODEs were actually super helpful in finally understanding electronics. Once you actually learn how to derive common equations yourself, it makes a lot more sense. I couldn't agree more. I feel so much more secure in my understanding of something when I can derive it myself. Homotopy principle of differential equations. I couldn't tell you what that is off the top. Could you describe it? Sounds interesting. Look. You need a third order derivative because the acceleration is increasing while the fuel mass decreases. That's right. This m is no longer constant. And then all sorts of things go crazy, right? It gets harder. I feel like I should save the catalyst, but burn the piercing whale. Oh, should I use one of these? I'm looking at a link now. Hey, Gromov, one of my favorite mathematicians. Holonomic solutions are the solutions to your A PDE satisfies the H principle if any non-holonomic solution can be deformed to a holonomic one in the class. Oh, like staying within the class of non-holonomic solutions. Thus, in the presence of the H principle, a differential topological problem reduces to an algebraic topological problem. This means that apart from the topological obstruction, there is no other obstruction to the existence of a holonomic solution. The topological problem of finding a non-holonomic solution is much easier to handle and can be addressed with the obstruction theory for topological bundles. It sounds very interesting. Of course, I know nothing about it. Somebody asked upstairs, where was it? Kappa votes. Yeah. What's the field of algebraic geometry / topology about? So first of all, algebraic geometry and algebraic topology are two separate things. Very different in character. Not totally unrelated, but very different in character. So algebraic geometry, at least the easy surface level cell or description, I would say, is studying solutions to systems of polynomial equations. But it gets way more deep than that. Like very quickly, so solutions to polynomial equations are sometimes called varieties, but it gets much deeper than that because, and this was a pretty recent revolution in the 20th century, with mathematicians like Grothendieck and Serre. You had a reformulation of algebraic geometry in terms of much more complicated structures called schemes. And that made I think the applications, let's say, of algebraic geometry to other fields, like it kind of exploded after that point. In terms of the power, I guess, and flexibility of this new way of viewing algebraic geometry in terms of these schemes. Schemes being, well, it's complicated. I don't even really feel comfortable talking about them because this is not my field. Yeah, but things really changed in the 20th century with Grothendieck. Grothendieck is a very interesting personality as well. Now, algebraic topology, I would say, is well, it's a very, very broad field encompassing a lot of stuff. But let's say we can talk about what you would study in, let's say, an algebraic topology class. The prerequisites for learning algebraic geometry properly are probably abstract algebra and maybe a bit of topology, like point set topology. The treatment that you'll often find, I think, nowadays is probably, you'll probably want to know some category theory too. I mean, yeah, I think that's true. With algebraic topology, in principle, I suppose you could just do that with some abstract algebra and some topology. Is this the exact same thing? Yeah. But like the algebra that you do in algebraic geometry is very much about rings, commutative rings, and that sort of thing, I would say. Whereas in algebraic topology, it's mostly about groups, abelian groups and such, and non-abelian groups too. Because in algebraic topology, what you're studying are certain algebraic, what are called invariants of topological spaces up to what's called homotopy equivalence. So there are these things called homotopy groups, which are a sequence of groups which you can associate with a topological space. And if you deform, or if you transform the space by doing something which, I don't know, it's hard to describe. It's called homotopy equivalence. Like if you were to just sort of like put an antenna or something like that, attach an antenna to to a topological space, it kind of feels like maybe you're not doing something super important to change that thing, because you could just kind of push that antenna back down into the topological space, if you know what I mean. So though the spaces may not be homeomorphic to one another, there's what they say a homotopy equivalence between them. Anyway, so algebraic topology is in the business of trying to distinguish topological spaces up to homotopy equivalence by using algebraic invariants like homotopy groups, but also like homology groups and cohomology groups and that sort of stuff. I would say that, well, I don't know. I don't know that I would say this, but yeah, that's sort of a very brief overview. Algebraic topology can, I think, be tackled by, I mean, an intro algebraic topology or intro algebraic geometry. I think either one could be tackled by a novice. Sorry, not a novice, but like a math major, maybe in their senior year. But I think it's much more typical that, or I think it's typical that a first exposure to these things with any sort of real depth happens in graduate school. Correct me if I'm wrong on that. I don't know. That was certainly my experience. What did I say I was going to do? How come it looks like orichalcum's not going to proc? Did I play a card? I have 5 cards. I don't understand. I don't think so. Okay, so it shouldn't be a problem, but... Anytime, Kappa. If anybody else has some questions about math or about anything else, just let me know. Or let us know, rather. Yeah, it doesn't matter. I don't need that. I wish I had a well-laid plans, because then I could keep this card. Not sure what I did, why I did what I just did, but whatever. Oh, it doesn't? Okay, I believe you. It's got 18. I win. Cultist potion. Gain strength at the end of my turn. Oh, this one right here. This card is incredible. And these... This one is... I think it takes a lot of work to make this one work. But this one... Yeah. Okay, another hard decision. Gain glob at the start of my turn. Future card rewards have 2 less cards to choose from. Oh. This is the one that I remember killing me all the time. So I can't take that because I'll just die. Double the effectiveness of potions. Yo. Like, so this would give me 2 ritual, and this would give me 10 dexterity, and I wait. Wait. Does this double the penalty as well? Do I gain 10 and lose 10? It feels bad to get 2 less card rewards. And do I need a 5th energy badly enough that could be justified? All right, let's see. Who's my opponent? Oh, this is the guy that when you use powers, it gains strength. And I know I have noxious fumes and after image. These are my 2 powers, so this is actually a good fight for me. I need the blue thing. What does the blue thing mean? Where does one get... Does one pick that up from a chest? Yeah, I'm pretty sure. So I don't need to worry about keys or super elites or anything like that. Here's 3 elite paths. One, 2, 3. Another 3 elite paths this way. This has 2 campfires. They're kind of nicely situated. Another campfire here. Whoa, what? 1? What? This has 4 campfires. You know what? But actually campfires are not very useful to me. Because, I mean, they're useful for resting. But I can't upgrade because of my stupid thing. Later, Uncle Bill. Thanks for stopping by the way. You know what? I'm gonna I'm gonna do some real networking here. We'll see what happens when I do this. So for example, let me get the stream URL. Copy. There's a math Discord with a bunch of folks in there. I don't know what their rules are on self-promotion or if there are any rules whatsoever about self-promotion. But I thought maybe I would post it up there. See ya, FS Rooster. Have a good night. Thanks for stopping by. Thanks for hanging out. Let's see. Well, if I get chastised, I think that's okay, but we'll see. I'll put this in the general discussion of this channel. Hi, I'm streaming a math question and answer channel on Twitch. Come by if you like. Come on by. I'll just say that. Come on by. And let me just see one thing real quick. Like, what is my nick on this? Might want to mention credentials. Oh, okay. Come on by. I sometimes forget to do that sort of thing. Thanks for the advice. I will take you up on that advice. Good. This is my name. My name on here is Ball, I believe. Yep. Shoot, I can't change my name on the server to reflect my real name because I'm using like some Discord name or whatever. Oh well, that's okay. My real name is appearing there. Okay, here we go. We'll see what happens. Oops. That's really big and ugly. I hope it's okay. I'm not sure how I feel about that feature of Twitch. Or sorry, of Discord. Hello there, folks. Yeah, it does a link preview. And it's this big old garish thing that gets stuck in the chat. And I can't imagine that it's pleasant for people who are having conversations, although I think I've picked a good little lull in the conversation in this general discussion channel to dump it into. So hopefully we're good. Anyway, hello to folks out there. This channel, the intention, the hope, the dream for this channel is that it eventually becomes a place for, it eventually becomes a place for the giving and getting mathematics. Hello there, emergency temporal shift. Oh, non-dairy neutrino. Thank you so much for the raid. Hello there. And welcome to everybody from that channel. Like I said, the hope for this place is that it eventually becomes a place, a community for the giving and getting of mathematics, knowledge, expertise, and questions, and that sort of thing. So if you have any questions about math or anything at all that you're interested in, thank you very much, Max Headroom and Adam all together. I noticed that I'm covering up my nifty little Stream Labs Twitch alerts thing. Oh, hello, Physics O. Good to see you. But if you are interested and you have questions about math and things, please drop them in chat. Will I be around here in an hour? Actually, I'm thinking I'm probably going to have to log off in about 26 minutes. But then come back on. And you know what? Maybe I'll extend that to 56 minutes. 5:30 sounds reasonable my time. But I will be on later tonight. Oh, you're drunk. I've been there. I know what that's like. I can relate. But if you have a question now or in an hour, hopefully I'll be around to answer it. But I've been trying to stream pretty regularly for the last 6 days or so. And I don't know. I hope to keep up a fairly regular schedule, put it that way. Yeah? Oh, you saw me on Reddit. It seemed like a lot of people saw me on Reddit. I think that's really cool. Not a tremendous number, but you know. I appreciate you. Thank you for stopping by, though. And you know, the question doesn't have to be like some highfalutin, super sophisticated math question or anything like that. Here, we're interested in questions at all levels. Be they simple, be they complicated, all that stuff. Thank you so much, Non-Dairy Neutrino. I'm going to have to check out your channel. Thank you very much. Yeah, but that's sort of what we do here, yeah? We do math stuff. But, you know, if there's something else that you want to talk about, you go right ahead. So what's going on the screen? This is the game Slay the Spire. We're just doing that to kill time when we aren't in Slay the Spire mode and we aren't trying to kill time and we're actually talking about math. The stream looks a little bit more like this. As you can see, we've been doing some calculus over here, some differential equation stuff over here. So we've got a pretty good variety of questions. Some people have been asking about, some calculus questions, like Calc 1 type stuff. And people have been asking about arithmetic sequences. We've had a question there. And all questions are welcome. Really. We have some rocket science discussions happening about what the trajectory of a rocket, which is accelerating while losing mass, how that should be modeled using a differential equation. Literally rocket science. But like I say, doesn't need to be rocket science at all up in here. Even very simple questions like how do I solve 3x plus 5 equals 8 are totally welcome and appreciated. What's the highest order torus I've ever worked with? The funny thing is I feel like I can answer that question. I feel like the 3 torus is the highest order torus I feel like I could work with. That I have worked with, rather. The 3 torus is really cool, by the way. Did you know, the 3 torus you can think about as, you know, you take a rectangular box like this. Let's just make it a cube for fun. You've all seen cubes before. But maybe one thing that you've not thought about is what it would be like to live inside of that cube. So imagine yourself inside of that cube and you're wearing like a jetpack. So you can move in all 3 spatial dimensions inside of that cube, okay? And you can imagine that when you go this way, when you go to your right, you can imagine that once you hit this wall, well, it's not really a wall there. What happens is once you go through that rectangle there on that side of the cube, you emerge on this side of the cube like this, right? So topologically, what that means is that you're going to take this right-hand side from our perspective, this right-hand side of the cube, and glue it to the left-hand side of the cube. So you can literally imagine taking this, stretching it out, pulling it around, and then gluing it to this side. And you can do the same thing with the 2 other pairs of sides, for example, the top and the bottom. You can imagine that with you and your jetpack, if you fly straight upward, that eventually you'll come out through the bottom of the box, you know, and return to the position that you were originally in. And similarly, you can move forward in this box like this, right? In this direction, like that. And you'll eventually emerge from the back of the box in the same position you were. So what you need to be able to do and imagine in order to properly see this space is to glue these 2 sides of the box together, glue the top and the bottom of the box together, and glue the front and the back of the box together. And if you can do all of those things, then what you've obtained is what's called in general a 3 manifold, and what is in particular a 3 torus. The 3 torus is also sometimes denoted T3, and it so happens that T3 can be viewed as a product of S1s. S1s here just being circles. So this is a circle, and this is a circle, and this is a circle. Greetings, friends of space-ignoring portals. I don't get why either. I've never studied Fermat's last theorem before. I couldn't even tell you what a Galois representation is. I can just barely blubber out the statement of Fermat's last theorem. If it's not clear, number theory has never been my strong suit. If you want something more elementary, of course, you can think about T2, which looks like this, the surface of the donut. Great question. What happens if you rocket pack into a corner of that cube that you described? So if you go into, like, let's say this corner right here, you'll emerge at that corner over there. Right? Like if you come in this way, come in hot that way, then you'll re-emerge inside of the box over on this side. What is a regular physical donut torus in relation to this T3 torus? Good. So if you want to, so what you can do is think about just one of these faces. Let's say. It doesn't have to be a face, but this is just one place where you can see a torus. If you see a face like this, and you think about how the gluing that we've just said, where you glue top and bottom, back and front, and left and right, if you think about the effect of that gluing on this torus, what you see, on this square, it's a little bit hard for me to talk, then what you're seeing is this square. I'm going to draw it sort of facing you. This side here gets glued to this side. That's sort of denoted like this. And this side here gets glued to this side, right? And this is actually a lot easier to imagine. if you glue this square so that this edge right here gets glued to that edge, just do that first, then what you see is like a toilet paper tube, right? Like this. That's one gluing. And then what you're going to do is glue this side to this side like this, and what you get is the honest to goodness torus. We denote this torus T2. T1 would just be a circle. You wouldn't split into the different faces if you hit a corner. No. No. So like part of you, like when you have size, right? So when you are passing through this corner, part of you is going to be passing through this face, and therefore you're going to emerge in the back. Part of you is going to be hitting this side face right here, this face on our left, and you're going to reemerge on the right. And the last part of you will hit this bottom face, and and that part will reemerge from the top. But you'll reemerge in a completely coherent way, like you're all together. You are all in the same. You're the same human being that you were when you passed through. What's interesting, well, I don't know if this is interesting to you, but it's interesting to me, is what happens if you take the same kind of picture of gluing up the sides of a square. Okay, so we said this gluing, where we glue this side to this side and this side to this side, like this. This gives you T2. But what happens if you glue slightly differently? So let's say we were to glue this side to this side. But then when we glue this side to this side, instead of gluing it like so that, you know, sort of in the straightforward way, we find ourselves needing to put a twist in it, so that we glue this side to this side, but we twist things up so that these arrows correspond, right? So that there's a sort of a flip in the correspondence or the gluing of these two edges, right? Then this takes some imagination, maybe. Can anybody guess what that kind of gluing results in? Almost Mobius strip. It's kind of like half of a Mobius strip in some sense. So a Mobius strip would be given by this. Let's see. Like where you take the top and you glue it to the bottom. This is and you do nothing to the sides. This is a Mobius strip. Mobius. Right? This is that common construction where you take a strip of paper. You take a strip of paper, you give it a twist, and then glue the two sides together. That's this. What does this gluing here give you? Has anybody heard of this this object before? It's called a Klein bottle. That's sort of interesting. I don't know if anybody's ever heard of this, but this is a famous example of what's called a non-orientable surface. And furthermore, it has the distinction of not being embeddable in R3, meaning that in order to see this object, you actually have to have a four-dimensional space to embed it in. And I believe it's embeddable in four-dimensional space. I have to draw it. Oh God. So here's my terrible rendering. Here's going to be the top. And it'll come around like this, and then there will be a little hole. This hole is special. You can't really see that dottedness. So this right here represents it looks like a self-intersection, but it's in four-dimensional space. It's not actually a self-intersection. And then it comes around like this. And then this little tube here comes back and joins up with the inside of the bottle. This is interior to the like that. Oh, one sec. Oh, you do? Okay. Um. Oh boy. Okay. Can you give me like 10 minutes? Esther, can you give me like 10 minutes? Yoshi's in front of the door. I don't know why. Yoshi, can you move? Can you give me like 10 minutes? Yeah. Sure.
What are you doing down there, Yoshi?
One of the circuits in our house just went out. Sorry. So I got some questions here. That's my attempt to draw the Klein bottle. Rate me out of 10, please. Someone asks, Laura JX asks, so if you were inside either that donut or the cube with the sides glued, how would you ever see the difference? To you, the inside of the cube or donut, you wouldn't be able to differentiate between them, no? Well, so this is a three-dimensional space, meaning that when you're inside of this T3, the local space around you feels three-dimensional, just like our real universe does, because we have three spatial dimensions. But on T2, we don't consider the solid donut, right? We T2 refers to only the surface of the donut, which is why we're able to craft it by gluing the edges of a two-dimensional square. This 2 here is meaningful, right? The 2 here and the 3 there are telling you about the dimension of the surface. So the way that you would differentiate between whether you are inside T2 or T3 is to count dimensions. And to really know if you're in, like, let's say a T3 versus like a regular old boring R3, which is our usual intuitive picture of what space looks like, you would fly around inside of T3. And if you found yourself flying in a certain direction for a while and then returning to where you started from, you might begin to be suspicious that you're not actually in R3. And I've told this story on stream before, but maybe 15, 20 years ago, there was a bit of speculation that maybe the structure of our universe was something more like T3 than R3. R3 being, denoted like this, being boring old, I don't know if this is boring, but like the XYZ space that you know and love. There was speculation like 15, 20 years ago from cosmologists that maybe we had a universe. We were living in a spatial universe that looked something more like this. This was not one of the proposed things, I don't believe. And rather, you can do this kind of construction for other polyhedra other than the cube. You can do it for like a dodecahedra, for example. And I think that was the example that was proposed. But it turned out that after examining, and I don't know the details here, I just know the little story, which is that they looked at the cosmic background radiation data and they said, probably not. I think that has something to do with like the curvature of space, and it didn't fit the data. Like it looks like after they did all the crunching and stuff like that, it looks like the curvature of space, or the curvature of something or other, is more or less zero. It's not there's nothing conclusive could be said, I guess. Nothing interesting. So T3 is that one scene from Interstellar. So the scene from Interstellar that I remember, and I don't remember it well, is that there was a 4-dimensional space that the dude was flying around in. Right? He was supposed to be in four-dimensional space-time there, I believe. And so he was able to sort of traverse the time dimension to like go back in time and such or something along those lines. So I would say T3 is not like that, but maybe there's a part of the movie that I'm not remembering. To complete this picture right here, before I stop thinking about it, there's one more thing that you can do, which is have both of these things reverse in direction, like that. So, what does this mean? This means that if you're a little ant and you're crawling around on the surface and you decide to penetrate this wall, where you're going to reemerge is over here. And actually, not only will you reemerge over here, okay, but everything will be reversed. Like your heart will be on the other side of your chest, okay, and that sort of thing. Your left hand will become your right hand. Any tattoos you have on the right side of your body will appear on the left side of your body. Okay. I mean, that's true about the climb bottle when you climb up here and reemerge over here. Yeah, T3 is naturally a flat manifold. That's right. This thing, it's hard to picture. Nobody's going to question that. But this is called the real projective plane. And amazingly, what you can do is you can identify this guy with, the set of lines passing through the origin in R3. So if you imagine R3, you can think about all lines passing through the origin, and there's a way of thinking about that as a space itself. So the space consists of points, and those points are represented by lines in R3. So like you can think about what we might mean by like 2 points being close together in this space. That's the process that we call making this kind of set into a topological space. And it turns out that this space, which is the set of lines passing through the origin in R3, is the same as this gluing up of the square. And actually, it's not that hard, if you're clever, to really see this identification. It's kind of fun. But if T2 is a continuous surface, then no boundary exists. So this one here, that's right, there's no boundary to this guy. And then there's no point where the flip occurs. This is topology, yes. I'm not sure what flip you are referring to, Lara JX. There's like if you're an ant and you're living on T2, you're never going to have that thing happen where the heart ends up on the other side of your chest. Right. That only happens in this particular case with the real projective plane. Like imagine that you are a being whose shape is the letter R. Okay, this is like your shape. Not the letter like this. There's no meaning to the letter R here. This is a shape, okay? And imagine that you're an R-shaped ant. This is getting really weird, okay? But imagine that you're an R-shaped ant and you march as an R-shaped ant past this wall here. How do you emerge over on this side, right? Well, because this wall here is being glued to this wall, to this edge. Sorry, you can't see any of that. Because this edge here, when being glued to this bottom edge, gets a flip, you're going to flip. You're going to emerge from the wall looking like that. Does that make sense? This is what I mean by your heart ends up on the other side of your chest. Yeah, the ant doesn't see or feel anything. True. And you know, the interesting thing also is that if they keep going, right? If they keep walking in a straight line, then the ant hits this wall, comes out here, and then when he goes through this wall, the ant flips again and it looks like this, and then comes back to where it started. It's not different from the looking glass. Sorry, I'm reading things and saying things at the same time. I'm bad at that. It's not different from the Klein bottle in the sense that this same sort of phenomenon happens here. But now in the Klein bottle, what we see is these two sides, the left and the right side, are identified kind of normally. The real projective plane is identified abnormally with a twist. Hello there, friends. Unfortunately, household duties call. And I have to be a family man for at least a while. But you know what? My plan for tonight is to come back and do another stream in the evening. Right now it's 5 o'clock for me. But my plan, and I hate to cut this stream here, but like I said, there's some stuff that has come up and I need to come back. Thank you for reminding me. Raid. I'm going to raid somebody. Yes, yes, yes. I'm going to raid somebody. I have to figure out who that is. If somebody has suggestions for who I should raid, I'd love to hear it. Cool. I'm so glad that I love this stuff too so much. I love this stuff. So I'm really happy that you all like it. Or at least that Laura JX likes it. That's enough for me. That's more than enough for me. But listen, my plan is to come back later tonight, probably in an hour and a half or 2 hours. If I lose some of you, that's okay. Know that I love you all. But if you do want to be alerted as to when I come back on, you can follow. No big, right? Is it a big deal? I don't think so. Just press that follow button thing, and you'll get an alert. Yeah. I trust non-dairy neutrino to point me to the good ass streams that I should raid. Thank you very much, the duck, though. I appreciate the follow. Hey, look at my funny little thing, Streamlabs. It's a raccoon doing math and having a great time doing it. Yeah, so let's do this thing. Let's raid somebody. I did this once, and I know it's a good idea. I know it's good practice, best practice, right? But I keep forgetting to do it. You are a trusted voice. I trust you somehow, non-dairy neutrino. What am I doing? I'm raiding, meaning that I do this thing. Raid. I almost typed non-dairy neutrino, but I really should be typing rock it sage. There it goes. All right, people. I love you all so much. Thank you so much for hanging out. This has been a great stream. 4-hour stream. I'm going to stream again tonight. So if you got math questions or anything, and again, doesn't have to be all sophisticated and crazy. Even simple questions are more than welcome. But come at me. Come at me tonight. All right. In about an hour and a half to 2 hours. Okay. All right. I love you. Bye. Let's raid. All right. Awesome. Thank you so much, non-dairy. All right. Here we go. Is it working? Yeah. Oh, yeah.